Hello everyone, David Ostrowski. This is week 12, continuing chapter 9 in MCS 2534 data structures. In this recording, I have yet another presentation dealing with graphs as an abstract data type, going through some examples, and hopefully this will help give you kind of take a step back and go through some of the basic concepts once again and step into it from a different angle. And hopefully this will help you understand the chapter 9 material a little bit more. You should be reading the book and also give you a better idea how to approach the programming assignment 4, and if you have any questions about that. So let me get started. Let's start once again with just the basics here. A graph contains two major components: a set of vertices, consider them the nodes, as you might see here in the left hand side, and edges, or the links between those nodes. So it's interesting to note, right? You have a graph. It may not be completely connected as this graph is, and this is, when we look at a tree, and we've gone through trees already, trees are nothing more than unrestricted graphs. Okay, so trees are a form of graphs. So it is interesting to note where the Venn diagram overlaps here, and that some of the qualities are shared in common because one is a form of the other, right? So some of the basics here: a complete graph, that's where there is an edge for every pair of vertices. Two kinds of graphs: directed and undirected. Okay, undirected is just simply connecting the related nodes. Directed may be the functional equivalent. Sometimes it is the absolute equivalent of a one-way road, right? That you can only travel in one direction or both directions, but it can be restricted, okay, as such. That's what we call it as a directed graph. And that's in comparison to, again, what is referred to as undirected, where the edge, let's say from V2 to V8, so you see here, it's the same as V8 to V2, right? I can go from either direction, either as a starting point going to the other side. So that's the primary distinction. So directed graphs, as you see here, it can be referred to also, has been, as a digraph, okay, where the edge is a set of ordered pairs. And even if the edge UV is present, the edge VU may be absent. I may be able to go to V2 to V8 as I can, as indicated by this diagram, but I can't go the reverse direction. Okay, so that's the direction. And again, this kind of a further restriction on graphs, and this is leveraged to great utility given the application domain, right? If I have weights associated with the directions, and sometimes, let's say, even you have a geographical equivalent, or you go trying to model something of a geographical nature. If you're going uphill, okay, it's going to have a higher cost associated than if you're going downhill, right? You just look at from the perspective of traveling in a vehicle. So that may necessitate different connections, and it could be directed. And again, there's no law here that's going to say that, well, you can only have one edge per the two nodes. So from that perspective, there's a lot of interesting angles that we could pursue with directed graphs given a specific application domain, right? A little bit more in the terminology, and this extends a little bit more than what we were exposed to in the last presentation. That a vertex W is adjacent to V if and only if V and W is in E. Okay, so if I'm going to have an edge between them, then they're termed as adjacent nodes. Well, in this case, V2 to V5, V2 to V8 would be adjacent nodes, and V2 to V3 wouldn't. Okay, so That's a suitable description. The weight is the cost parameter associated with each edge. That could mean any number of things in the real world. Obviously, not all paths towards the solution of a problem are equivalent in many cases. Some are, some aren't. Okay, so in this case, you have the ability to express a different type of weight associated with that, right? So next, the path is a sequence of vertices where there's an edge for each pair of consecutive vertices. So V7, V8, V6, V3 could be a suitable path, right? I'd be going from those nodes moving forward to 7 to 8, 6, 3. I can't go 7, 8, 6, 3, 4 because 3 is not connected to 4. So that wouldn't be a suitable path, right? Length of the path can be calculated as the number of edges along the path and the length of the path of the vertices of n vertices. If I have 3 vertices on my path, right, the length is going to be n minus 2. And correspondingly, the cost of that path would be the sum of the weights of the edges that follow along in that path accordingly. So if I were to go from V7 to V6 via V8, I could go through the other nodes. Probably be, in most cases, obviously would be a more costly path, but that would be the path of 5 because it was 7 to V8, where the cost would be 1, and V8 to V6 would be 4, and I add that along the path, and you keep on adding it as you go along. If I went through 7, 8 to 2 to 5 to 3 to 6, then it would be 1, -1, right? 5, 2, and -2. So actually, it would be the same path, interestingly, because I have the negative costs associated with that. So costs are there for a reason, right? Because at first glance, you may think that the length is associated with the cost, and that's simply not the case, as we see in this simple example. So the two need to be differentiated appropriately, and that's where the cost plays a substantial role, right? So cycles, okay, if we look at cycles are determined where you can have a path that simply cycles around. So a path is simple involves vertices are distinct, except the first and last may be equal. Okay, a path from V1 to V4 would be a simple path, right? Because there's no other way to approximate that. If I were to go to V7 to V6, and I have 2 paths, and I can also be a generate a cycle here. So above the V28 6352, and I look at 28 6352, I can go round and round and round and keep on going around that. So that's a cycle determined in the path. I can keep on repeating the path and getting to all the associated nodes, even in the directed graph, right? Breaking down the terminology a little bit further, an undirected graph G is connected if for each pair of vertices U to V, there's a path that starts at U and ends at V, right? The digraph that satisfies the above condition is strongly connected. That means from any node, I can get to any other node. It may not be the most cost effective, right? But I can get there, right? So because there's a connection, there's a path from each node to every other node that's indicated, right? And that's a comparison to the example that we saw 2 slides back, where it's not strongly connected, right? If I'm in V8, I can't get to V4 by any other means, right? So this speaks to the last point here. If H is not strongly connected, But the undirected graph, the same set of vertices and edges is connected, then it's correspondingly would be indicated as being weakly connected. So weak, and with the WEAK, right? So representations of graphs, two popular representations. I have an adjacency matrix and adjacency list, right? The matrix is your Boolean-based representation. And I spoke to this earlier, right? And the list is the pairwise node to node through one edge, and all the pairs being added together is going to be the associated list. So with the adjacency matrix, it is AN of n subtracted by the big O of n squared space. And the AU of v is true if there's an edge from U to V, right? Or false otherwise. So it's just a Boolean representation, right? For a weighted graph, you can assign a weight of, and in an undirected graph, you only need half the matrix, right? So if you have goes back to the earlier point, right? U to V edge is equivalent to V to U in an undirected graph. In a directed graph, I would need the complete matrix, and that would get back to the order n squared, right? So base representation. Adjacency list, each node maintains a list of neighbors, adjacent nodes, and they take O vertice plus edge space. A couple approaches, more than a couple, but we see two that are indicated here. First of which, a hash table can map the vertices to adjacency lists, and the second approach, a vertex structure maintains a list of pointers to other vertices. And here's some graphical representation of the graphs. So here again, this is a directed graph. It necessitates an complete matrix. If I had undirected, it would be essentially a mirror reflection. Okay, if we're going to go across the left-right diagonal from top to bottom. But this is directed, and we see that with the associated arrows that are indicated here. And I have the true, as I see here, 1 to 2, 1 to 3, 1 to 4 are all trues here. 2 to 4 and 5 are indicated as such, and everything else follows, and anything that isn't pointing to 4 doesn't go to 6, 5, 6, or 7, or itself. I could point to it, it could point to itself. It doesn't, so in that case, it's indicated as false, right? So, but you can see, and it's really a function of really how many edges that you have, right? That the adjacency list in this case is relatively small. You could argue that it's not that much smaller, but it allows for the means of, in many cases, with not a lot of edges, less of a little more of a compact representation. But both of these, the adjacency list and matrix, are functionally equivalent to each other, right? Topological sorting. So a G can be a directed acyclic graph, or DAG for short. The topological sorting is an ordering of vertices of G, such as if there is an edge from Vi to J, then J appears after V to I. And here's one topological sorting that can be occurred here. And I have the top here, I have Mac 3311 and COP 310. I'm working from the left, right? And you can see that we are sorting it in the means of direction. And from each of the initial row, so Mac goes to the MAD 24, and then cop goes to the cop 3 goes to the same, but it also goes to 340 and 337, right? And the MAD 2410 correspondingly goes to the cap 3011. So here I'm working with the fact that I to J, okay, then J appears after I, so my initial graphs would be indicated in an ordering that's in alignment with the actual direction. Okay, so something to consider towards the sorting. So here's a little bit more on the specific algorithm that's applied. So in a DAG, there must be a vertex, no incoming edges. Here we'd have each vertex maintain its in degree. In degree of V indicates the number of edges from U to V. And here you would repeat to find a vertex of the current in degree 0, assign it a rank, and reduce the in degrees of the vertices in its adjacency list. So working through the algorithm, top sort, the counter goes to the number of vertices and then increment accordingly. And in each case, I find a new vertex of in degree 0. If it's not a vertex, I throw a cycle found exception. And then I assign the counter to the top num. And for each vertex W adjacent, I would decrement the in degree for that given vertex. Continuing on with the topological sort, here I have a templated queue of the vertex data type and a counter, and I would make the vertex empty, and for each vertex V, if the in degree is set as 0, I would unqueue V in the queue, and while the queue is not empty, I would do a dequeue from the queue and assign that to V. I would increment assign the next number to the top, and for each vertex W adjacent to V, I would decrement, and here I decrement before comparing it to 0. That's where the negative is before as opposed to afterward, and has precedence in a evaluation in the context of C++. And then I would enqueue it into the queue and perform a check at the bottom. If it is not equal to the number of vertices, then I would throw the appropriate exception. Single source, shortest path problem. So here, if I give it a graph, V with the associated vertices and edges and a distinguished vertex S, find the shortest path from S to every other vertex in G. In this case, I would use unweighted shortest paths, a breadth first search, or a weighted shortest paths with Deicher's algorithm, assuming no negative edges in the graph. Unweighted shortest path example, here I find the shortest path from V3 to all of their nodes. Okay, so V3 here is at the left, and I have just 2 outgoing. It's a directed graph, so I'm going to go to V1 and V6. And here, we're going to look through explore the variations here. If I have the example with 1, okay, I have the 0 on the associated node indicating the V4 to V3, and then going from V1 to V4 is a cost of 1, and 7 to 6 is 1. And then continually moving through the algorithm, I have the cost of V4 to 7 is assigned to 2, and similar nature, V2 to V5 is assigned to 2. And then in the fourth, and the lower right hand side, right, from V5 to V7 is a cost of 3, and correspondingly from V7 to V6 is associated of 3. Next, doing an implementation on unweighted shortest paths. I'm going to unweighted for each vertex V if the distance is set to infinity, okay, and the node is false. That's my starting point. So they're all set to infinity. And obviously, when you're complete, you're going to have something less than infinity for a reachable path, right? So for the current distance is set to 0 and falls less than the number of vertices for each vertice. Given that it's not known and the distance is equal to the current, then I would set the known to true for each vertex W adjacent to V. If it's set to infinity, then I would increment the distance appropriately and assign that vertice to the associated path. Next, we presented improved methodology here. We separate the unknown nodes with the minimum distance and using Q to track the nodes to visit. Get the complexity of big O edges plus vertice, and we follow the associated algorithm unweighted, where I'm passing in the vertex S. So for each vertex V, I set it to infinity. I set the distance of S to 0 and Q it. And while the Q is not empty, Q is empty, right? I'd set the DQ it, set that to V for each individual V. For each adjacent vertex, okay? If the distance is infinity, I increment the distance appropriately and set the path to the associated variable, and then Q the associated weight. This is in comparison to Dijkstra, so the weighted edge version of the previous algorithm called Dijkstra's algorithm for shortest paths. Here the process is equivalent, except the update of the distance function uses the weight of the edge instead of assuming it to be 1. So here you have all my weights are already assigned to the edges. Whereas in the past, I assumed, again, in the prior example, we assumed equal weight. So here we have a sample, and we're working through the separate movements. So let's grab our starting point. 4, 5, 2, 8, 1, 3, 4, 1, 6, 10, 2. So here the V4 is set to 1. Appropriately is the weight from V1, right? Which is at 0, and I cross the path to 1. So that's set appropriately. That's the only the difference from the upper left to the upper right. And then as I move forward, I'm assigning the paths, okay, accordingly to Dijkstra. And we're removing the infinity. You can see on the lower right that the infinity has changed 3, 5, 9, and the infinity is going to 3 associated. That's adding the associated weights for the most efficient path, right? Finally, going to V2 is starred, and that is the has the associated path of 2, and those are indicated appropriately with V4. Next, V5 is starred. Okay, and that's the upper left-hand side. It's continuing the example from the prior. As is V3, okay, in the right-hand side. And then V7, and then finally V6. The second example, leveraging the Dijkstra algorithm, is indicated with the following graph representation. And this is a little bit more demonstrative. So infinity is the default, right? We replace infinity with a finite path and a connected, obviously in a connected graph. I start with an A, and I go to D, and then A, D, E. And so the comparison with Dijkstra, okay, I think it's a little more illustrative in this representation. You are continually making a comparison between any of the earlier node explorations, right? So, for instance, I may be moving from B to C to consider my next move, okay, if this graph were larger. Why? Because the red has already established the connected, and they're already set up appropriately in the second column there. So, and this speaks to the fact that, right, you can be caught in a local optima, and not all of those is really indicated by even some of our easiest examples, that some of the initial representations just are not shortest path is not the most cost-effective path, right? And that's why we consider the short, because you can go through what is doing more of a greedy methodology and be blocked in, right, into a node that has a very expensive final path that you're considering among all available nodes to consider your graph. And the graph isn't just a straight line, right? So that a single direction, it could be going through separate paths as indicated through the red here. Here's the pseudocode of Dijkstra, okay? And in C++, the path would be the type vertex. That's how we indicate the path, is kind of indicated in the prior diagram. And that's indicated with the list, the Boolean type, the distance type, going to give us the distance variable, and then the associated path is defined as a vertex, right? Continuing on with the implementation, I have the Dijkstra, and for each vertex v, I set the distance to infinity, we set the known to false, the distance to 0. And it's important to note, right, that this is a pseudocode-based representation, that you really wouldn't use a for loop without any conditions, but they're just kind of saying, hey, just run forever, okay, and but you're going to identify a suitable stopping point in this case, right? So here the vertex v is assigned to the smallest unknown distance vertex. It's not a vertex, I do a break or some type of error checking. I would set the vertices known to be true. For each vertex, w adjacent to v, if it is known, you perform the associated test. The vertex plus the weight is less than the weight of the distance. Then I'll update w appropriately and do a decrease and assign the appropriate path. So this speaks to the point, right? The complexity depends on how the smallest distance vertex is identified. And the big O here is V squared. And with the priority Q, I would have the, as a heap, be evaluated as big O E log V plus V log V, and a Fibonacci heap with the big O E plus V. So I hope this helps. I'm going to be doing more videos. We're continuing chapter 9. And if you have any questions, feel free to reach out to me. Thanks for listening. Have a great week. See you in the next one. Thank you.